All right, so exactly what we just did for the magnitude, we're now going to do for the phase. Let me just actually write that up here. Might as well. Phase, mag, okay, and I think it would be helpful if I come and grab this transfer function that we broke up into the individual components here, and I'll just put it right here. And then I'll just delete these. Oops, the little gray circles. Okay, so we broke up our transfer function into these four factors, right? A constant gain of 10, an origin 0, a simple pole at s equals minus 2, and a simple pole at s equals minus 10. And so what we did in the previous video was we basically looked at the contributions of each of those factors. The constant here, the origin 0 here, and then the pole at 2 here, and the pole at 10 here, right? And then we added their effective responses to get one total response that is the magnitude response for this entire transfer function, which is really nice and really convenient. We're going to do the exact same thing now for the phase, right? If you remember correctly, each one of these terms had some magnitude behavior. It also has some phase behavior, so we can do the exact same thing. And we're going to start with the constant gain term. So the constant gain of k, if we go look at the constant gain, we can see that the phase of a constant gain is literally just 0 degrees for all frequencies. So that's super easy to start. We can just sketch. We almost don't even need to sketch anything there, but we might as well. It's just going to be a dotted line right along the origin at 0 degrees. It's not going to contribute anything to our phase, which is really nice. So we almost don't even have to worry about it, but I'm going to sketch it anyways just for the sake of completeness. This is my constant gain k, okay, which is 10 for this particular example. But you'll notice that the magnitude of the constant doesn't make any difference in the phase response. It only makes a difference in the magnitude response. Okay, so how about an origin 0? Let's go look at what the origin 0 has to say about the phase. An origin 0, for us, again, n was 1 in this example. It's just a flat 90 degrees response, right at 90 degrees. So let's go back to our plot here, and we're going to sketch a straight line right across the top at 90 degrees. And that's going to be the contributions from our origin 0, right? Okay, we're halfway done. We need to do these next two, which are the simple pole at s equals minus 2 and the simple pole at s equals minus 10. Okay, so let's go look at what simple poles look like. So this is the simple pole phase response. We know that it's going to be 0 degrees up until a decade before the pole, and then it's going to start dropping at 45 degrees per decade for 2 decades, and then it's going to flatten out. Okay, so the first pole that we have is p-value, p equals 2, and then we have another one at p equals 10. So we basically just need to draw two of these, one where this p-value is 2 and another one where it's 10, right? So let's go ahead and do that. So I know that they're both going to be 0. The first one's going to be 0 up until a decade before, right? 2. A decade before 2 would be 0.2. And then it starts dropping at 45 degrees per decade. So 2 will be at 45, and then 20 will be at 90 or negative 90. That doesn't look very linear. Let me move this tick mark down to make it a little bit better of a scale. It's probably better. Okay, so now I can connect those. And then I know that after 2 decades, it flattens out. So I can just draw this flat, right? And then the last thing I need to do is the same thing for the one at 10. So a decade before, it'll be at 0. It goes to 0. Then at the value of p, it drops to negative 45 degrees. Then it drops for another decade at 45 degrees per decade, and then it flattens out. All right, and so this is from my simple pole at s equals minus 10, and then this is from my simple pole at s equals minus 2. All right, so we have everything we need now to sketch the phase response of this transfer function. Okay, all we have to do is add the effects. And so again, let's look at the first interval here where nothing's changing. Nothing is changing from the origin out to 0.2, right? All I have there is a flat 0 and a flat 90 degrees. So if I add the 0 and the 90 degrees, just get 90 degrees. up until this point where something changes. What changes? We add the effects of this first pole, right? At point 2, from point 2 all the way out to 1, basically, so this range of frequencies here, I get 45 degrees per decade of slope. So I'm going to start drawing 45 degrees per decade of slope, which would lead me right to about there. It's not going to get me quite to 45 because I would need to be here to be at 45. So it's going to lead me right to here, where at 1, I get contributions from another pole at 45 degrees per decade. So if I have one pulling me down at 45 degrees per decade, another one pulling me down at 45 degrees per decade, then the net effect of these two poles is that I'm going to be pulled down at 90 or negative 90 degrees per decade. So now I need a much steeper decrease for the next decade, which is from 1 to 10, right? That's going to decrease to at about 90 degrees per decade. Now that might be even too steep. From 1 to 10, I need to get to like right here. And then I actually am going to keep drawing that until, what is it, 20? Yeah, 20 is where the first pole kind of stops and then flattens out. So that's going to go all the way until 20. And then once I get there, now the only effect that I have left is this minus 45 degrees per decade. So I'd be at minus 45 degrees per decade right until I hit the frequency. I think it's hard to draw these to scale sometimes when I don't have a grid. I wish I had a grid. Let me see, what did I do that's making this look bad? I think I really just need to... It should hit right around here. Let me just draw that line, just like that. And then it goes like this. So I have, this is minus 45 degrees per decade for this contribution from the first pole. Then once the second pole kicks in, I get minus 90 degrees per decade. So that's going to be this one. Okay. And then once the first pole flattens out and the second pole is all that's left, I get minus 45 degrees per decade again. And then the final value here is negative 90 degrees. Okay, so that's my phase response. I've now taken care of the magnitude and the phase response for this transfer function. So let me just add one more slide of the current template. And let's get our magnitude and our phase, and we'll put them together with the transfer function just for completeness. Okay, so I've got, let me copy this. I'll put that here, shrink it. So that's our magnitude plot. And then we'll do the same for the phase. Let's just grab all this. I got some gray in there that I want to grab. Let me get all that. Throw this in the next slide, paste. I'll shrink it quite a bit. Get it to be about the same size. That's our magnitude and our phase response for this transfer function. And then for one final piece here, would be nice to have our broken up transfer function there, so we can see that this is the goal of these types of problems, is to break the transfer function up into its factors, to plot the individual factors, and then to add up their effects to get the overall response. Okay, and so I'll just write magnitude here and phase here, and we would be done with this problem. Okay, so that is the first of the two examples I'm going to do. I'm going to do another example which is pretty similar. I'll probably move through it a little bit quicker. I'm still going to explain myself as I go because I know that this is probably still not 100% clear, but hopefully you're starting to see the gist of what we're trying to do here, and hopefully you're appreciating why it is that we would rather plot a transfer function this complicated like this, rather than trying to find the magnitude of this and plot it point by point. Because point by point is not, elbow by elbow. It's not talking about where all the changes occur. This is talking about if I wanted to know all of these different frequencies, I would need to plot all of these different frequencies, really. I mean, you could get the general shape of this thing with just a few points, but Again, as we get more and more complicated, as we move to higher and higher ranges of frequency, these plots can range from 1 hertz out to 100 gigahertz. And it's really just important to be able to understand these plots, to look at them and know what I'm looking at. Yeah, and we'll talk more about that when I do the next example. But we're going to leave this one here. Hopefully this makes sense. If you have any questions, please feel free to ask. And in the next video, next couple videos, I'm going to go ahead and do another example that's very similar to this one, go through the exact same process. All right, so I'm going to end this video right here.